Hi, we're from KKED. My name's Kurt. And today we're going to be performing an experiment for, let's get into it.
This is 1.5 centimeters. And then we'll be adding these two. One this side and the other one will be this side. We're using the center. Then first make sure this is level. So from right here and then from right here to make sure this is the center. And then we'll be putting this spot right here.
Cool. So when we're ready to actually perform the numerical part of the experiment, we're going to load up our capstone software as usual. We're going to drag in our simple graph and then change the axes to a position versus time graph, and also add a second graph and make that one a velocity. We can then perform our experiment. We have some ready off to the side, so I'm going to zero it out so that it scales it and then hit record. So we've already performed the experiment and we got a whole lot nicer of a graph than this, but this is just to show what actually goes down.
Alright, so for the first set of calculations for this experiment, we have to use the Pythagorean theorem, right, where we know that our right triangle can help us determine a certain angle, right, and we'll say this angle is theta. The angle opposite to that is obviously the opposite, and then the longest side of the triangle is the hypotenuse. We know that the distance, right, from the top of the table to there, it has to be 1.5 centimeters. And we know that the overall glider itself has a distance of 100 centimeters. So now, using what we know, right, and we got that because it's 150 centimeters from there minus 100, right? No, I'm sorry, minus 50. And that gives us our 100 centimeters distance. Then we can use this portion of the formula, right? Apologies, this portion of the formula, and solve for the sine theta. So again, we say that sine theta itself has to be equal to the opposite over the hypotenuse, and in this case, it's going to be 1.5 over 100. Continue solving for theta, right? Theta is equal to inverse sine 1.5 over 100. We plug this value in. We get that theta is approximately 0.86 degrees. And outside of finding what our degree is supposed to be, we can find our acceleration. And we know that our acceleration is equal to acceleration times g sine theta. And then we just start plugging in our values, right? 9.8 is our value for gravity. And then earlier we set it ourselves. Sine theta is 1.5 over 100. And then this gives us our theoretical acceleration of 0.147 meters per second squared. Now that we've added the new graph to the page of our experiment, we're going to select our velocity measurements and then calculate our acceleration and percent error based off of the velocity times time graph, right? And this is where we get that the experimental acceleration is obviously equal to the velocity, or the first velocity minus the second velocity minus the initial velocity, and then the initial, or the second time minus the initial time. When we plug in these values from our experiment itself, we have 0.57 minus 0.28, divide that all by 3.95 seconds minus 1.65 seconds. And that gives us a experimental acceleration of 0.126 meters per second squared. When it comes to the percent error of finding out how we actually did this, we understand that percent error is whatever our experimental was, subtract out our theoretical, and then divide that by our theoretical once again. So using the value from this time and the previous time, we can plug and chug these in. 1.26 minus 0.147. Divide that all by the 0.147, and that gives us roughly a percentage error of 14.2%.
So we got our angle for the surface, and then we got our mass and our real theoretical and our experimental acceleration. And now we're gonna add more mass, looking at our second acceleration. And we're gonna perform it again to get the second acceleration.
Right, so now that we've changed the mass of our slider itself, we're just going to re-perform the experiment and find now the experimental acceleration. So once again, zero it out and then hit record. And again, our graphs are much nicer than this, and we have performed the experiment.
Now that we've calculated that initial experimental acceleration, we're going to go ahead and add some extra mass to the glide in a balanced way, right? So just the same weight on each side. And then we're going to go ahead and rerun this experiment to get our new values. So now this is still the experimental acceleration, but I'll call it prime, right? And we're still using relatively the exact same formula. But now we're plugging in these new values given that we've since upped the amount of mass. So again, we start plugging in our values, 0.58 minus 0.28. These are our velocities. And then our new times, 3.85 minus 1.6 seconds. And then this gives us roughly a 0.13 meters per second squared acceleration. And this is our new acceleration given that we've increased the mass. Alright, so now we're going to change the tilt of the track. We were told to either take off or put on some slabs. In our case, we actually put on some slabs. And then now we're going to calculate our new theoretical acceleration, its percent difference from the original, and then find the one that has the lowest percent error. So we pretty much, again, have to use the Pythagorean principle. That was a bad triangle, but here we are. The Pythagorean principle, where we know we have some sort of angle that is opposite, correct? We know that this is our hypotenuse because it's the longest side. And then instead of it being 1.5 as previously mentioned, now it's going to be 3 centimeters tall. So we actually increased the height, right? This is still a length of 100 centimeters, right? Our hypotenuse. And with that being said, we continue to use the same formulas where sine of theta is still equal to opposite over hypotenuse. And in this case, we'll do 3 over 100. If we solve for theta to find the angle, it's still sine inverse of 3 of 100. And then this gives us roughly an angle of 1.71 degrees. That is our angle, but now if we try to find our acceleration, we bring back our formula. Acceleration is equal to gravity times sine theta of the angle. Again, plug in 9.8 as our value for our gravity, and then 3 over 100, given that we said that that is what sine of theta is earlier. And finally, this gives us an experimental acceleration of 2.94 meters per second squared.
And this to change our height from 1.5 to 3. And with this, we can find a new experimental acceleration, theoretical acceleration, and we have a new angle for our slope. And the mass remains the same on the ground.
So using the same position versus time and velocity graphs, we're going to repeat the experiment with now the new changed height, the new angle, and the same mass. So if we repeat these experiments, again, clear and hit record, we'll get the final part of this experiment, which shows us how much the angle changed. Thank you.
For our final set of calculations, we're going to collect and calculate the experimental values, and then we're going to analyze our changes with the new setup, right? And so when we rerun the experiment, again, we're trying to now find the experimental acceleration. I'll call this one experimental double prime. Once again, we bust out the original formula that has to deal with acceleration. And we'll go ahead and plug in these values, which we got experimentally from our graph, which is 0.88 minus 0.15, and then all by 3.4 seconds minus 1.35 seconds, and then finally that gives us a value of 0.356 meters per second squared. And so that's the experimental acceleration, right? And so with that being said, we can find the percent error. And the percent error is going to be our 0.356 value minus our 0.294 value, all divided by the 0.294 value again. Remember, it's the experimental minus theoretical divided by theoretical again. And that gives us roughly a 21% error. Thank you.
So when we change the mass of the glide, are we expecting to see a different acceleration, and why?
No, we're not expecting a different acceleration because the acceleration depends on the gravity and the angle of the glide.
Okay, so even though we've changed the difference in mass, is that going to change the difference in our percent error, and why?
I'd say it would, because since we add mass, it doesn't directly affect it, but because of the change in friction, it does affect the value.